Alright, good day guys, you're welcome again to my channel, and today we want to make an advancement on our previous tutorial on the foundation design, how to design an isolated pad footing, part 2. So in the previous tutorial we were able to obtain the base area, how to determine the size of your pad footing. Right, so from there we'll be establishing further details, obtaining our flexural reinforcement, and checking for our punching shear. Right, so we have two important things to do. um, First of which, to determine our flexural reinforcement, or to design for flexural reinforcement. And secondly, we're going to do a punching check, right? And we'll be done for today. Right, so but before we would go ahead, I would like to make a note following our previous designs on pad foundation. Right, so while we were obtaining the area of base, we applied the formula, the load, that's the serviceability load, divided by the soil or safe bearing capacity. Right, and there is an exception to this, or not in all cases would you apply this formula directly. Right, so you need to, and I think I made mention of that in the last tutorial, but as a matter of emphasis, I would like to highlight it again. So when you're dealing with the unfactored load, or you could just say that when you are using the service load, right, this formula is applicable, right? But when because the idea of foundation design in this case, actually, to obtain the area of this pad footing, we are supposed to use the service load. So you have to find your way down to the point where the service load will be applicable, and that's just the idea. So let's assume the loadings that we have obtained um, is the ultimate load on that acting on the pad foundation, right? So in order for us to obtain the area in this case, we will need to apply the allowance for the self weight, then we divide by 1.45 multiplied by the soil bearing capacity. Now with this 1.45 had somewhat removed or nullified the factor that had been applied to the ultimate load, so thereby leaving us with the unfactored load. Right, so that's simple enough. Or to highlight that, we know that for the ultimate design load, we have the 1.4 GK plus 1.6 QK. So if you obtain a value for this, by dividing the value by 1.45 should give you the unfactored load, or something very close to it that you can apply all through. Right, so to leave that and to go into a proper detail for today, um, we'd like to continue from here. Now to go straight into the design we have to do today. Right, the first thing to obtain would be the earth sprayer. We have to obtain the earth sprayer, of which I'm going to show you how exactly we do that. Secondly, we check the flexural reinforcement. And lastly, we do the punching shear. Now, so these are the three things we want to check out for today. Then we'll be done in simple steps. right? And I told us in the determination of our part base area, we actually apply the service load, that is the unfactored load. But in the case of obtaining the earth pressure, we would have to find the total ultimate load. Total ultimate load. And we know that that is obtained from 1.4 GK plus 1.6 QK. Right? So from there we'll have 1.4, and the dead load we obtained there, as said in question, 1050 plus 1.6 in bracket 300. So this automatically would give us 1950 kilonewton. Right? So to obtain the head pressure, like I said, the head pressure now, you use the formula, the ultimate load obtained divided by the base area, the one we calculated in the previous video. In case you had not made contact with the previous video, you can check my video playlist. You find how to design isolated part foundation, part 1. So you find the value for our base area and how we obtained all the values in that video. Right, so we have in that video, we obtained our base area to be 9 meter square. So we have 1950 divided by 9 meter square. All right, so our value we have should be 216.7 kilonewton per meter square. All right, so this exactly is the base area, and that's what we'll be applying all through our project. Now it's simple now, so we can move further. We have solved the first challenge. Now the second thing to find out or to design for will be the flexural reinforcement. Now in the design of a pad, isolated pad footing as this, the moment is always calculated using simple cantilever equation. So moment is calculated using simple cantilever equation, and we understand that the equation for cantilever, to obtain the moment for a cantilever, is WL square over 2. So in this case we would have 216.7, which is the pressure obtained here, right, multiplied by the length, and in this case it will be 1.3. What we obtained in the area gave us 3 meters by 3 meters pad footing. All right, and the thickness of our column is 400. Knowing full well that the dimension on the right will be the same as the dimension on the left, so we would have 1.3, 1.3. Right, so then that's why we have 1.3 here, right, divided by 2. This is square. So our moment here will be 183.1 kilonewton meter. All right, so we can just proceed from here, and we can just see, as we have in these diagrams already, our head pressure will be the one influencing the pad just from beneath, and it has a value as obtained 216.7 kilonewton per meter square. All right, And I already explained this to us. The base area obtained from the previous video is 3 meter by 3 meter, and we have a 400 millimeter square column acting on the base, right? So we have the same distance on the right and to the left, which is 1300 millimeters, right? And that's exactly what we have here. Now, having obtained our moment to be the moment to be 183.1 kilonewton meter, we want to begin to design. But before then, we need to obtain our effective depth, because we apply the effective depth in our design, effective depth D. And this is obtained by subtracting from the total thickness of your base. You subtract the cover to reinforcement, then you subtract the half of the bottom reinforcement. So for this, we are assuming 20 mm diameter reinforcement, right? So from there, and in the previous video, we already obtained the thickness to be 300 millimeter. That was our assumption in calculating for the self weight of that part base, right? So that's exactly what we're going to use in this case. And not to forget, from our BS 8110, the British Code of Practice, would from the table 3.3, which is for the cover to reinforcement, we can see that for the concrete grade, for this particular question is C35, right? And the minimum for that for this grade now. But what we are dealing with here is a foundation, which would be an alternation, or there will be an alternation between the wet and the dry condition of the soil, right? So it leaves the condition as severe, right? So, and that's why we want to take our cover for foundation design, for this design, to be 50, right? So our cover here will be 50 millimeters because of the severe condition, um, as a result of the alternation between the wet and dry condition of the soil, right? So from there we can obtain our H, our D rather, which is the effective depth. That's 300 minus the cover now, 50 minus the diameter divided by 2, right? So if you do this very well, you should have 240 millimeters, right? Now another thing we would need to confirm is the moment of resistance, right? The ultimate moment of resistance, and this is actually giving us an idea of how much resistance this concrete element can actually withstand. And if peradventure the moment as a result of the applied forces exceed the moment of resistance, it means that we'll have to apply compression reinforcement, right? So in this case now, to obtain that, we use the relation 0.156 FCU BD square, right? So we know our FCU to be 35, our B to be 1 meters, and our D as obtained here to be 240. So if we apply this, our solution should give 314.5 kilonewton meter, right? And the moment obtained in the previous application of our simple cantilever equation or formula, we have 183.1. So moment of resistance is greater than moment applied, therefore no compression reinforcement is required. And that's what I'm trying to say. No compression reinforcement is required. Right, so we can proceed then. To obtain the value of our K, our formula remains m over FCU B d square, right? So we know our m already to be 183.1 times 10 raised plus 6. Then the FCU we have to be 35, 1 meter for B, and the depth to be 240 square, right? So this automatically would give 0.091. So from here we can obtain the value of our Z from our usual relation 0.5 plus the square root of 0.25 minus K over 0.9 in bracket D. Of course, this should be less than or equals to 0.95D, right? Substituting the value of K into this, your result should give you 0.86D, which is clearly less than 0.95D. Right, so we can obtain the area of steel for this. Area of steel now will be m over 0.95 FYZ, right? And the FY particular for this question is 500, right? Right, so we'll have in application 181 or 183 rather, 183.1 divided by 0.95 Fy being 500 and Z has obtained 0.86 multiplied by 240, right? So this result should give, this is the area of steel required. So this result should give 1867.61 millimeters squared, right? So from here we can make provision, right? So when you check through the reinforcement tables, right, so you should be able to pick a particular reinforcement for this. But in the absence of that, you can also use mathematical relations to obtain what reinforcement and what spacing is suitable. But either of the two you use, you should be able to result to the solution to provide Y20 members at 150 center to center spacing, right? So here the area of steel provided is 2093.3 squared, right? So minimum area of steel now, to obtain the minimum area of steel, to be sure that our result is valid, we use 0.13% BH, which is 0.13 divided by 100 multiplied by 1000, then the thickness of the concrete base. So the result we have is 390 millimeters squared. Now we see that this value is way below this, and we are safe, we are good to go in this regard. All right, so in case you have any issue there, you can just use the comment section, as I'll be there to respond to you. And if you have not yet liked this video or subscribed yet, you can do that now and begin to share to your friends now to get better in structural engineering. So lastly, to obtain a punching shear, which is actually very important, so that you'll be sure if the concrete section will be sufficient to support the load and without the punching failure. right? So to go about that, we want to check for the critical shear, the punching shear, right? So to check for this, we know that the punching effect would take so much formation at 1.5 multiplied by the depth away from the column face, right? So as illustrated just here, right on your screen, right? So the first thing we want to determine now is the critical perimeter. Then we'll find the area within the critical perimeter. Then we would apply to confirm if our concrete structure, our base, is safe against punching effect, right? So for the critical perimeter now, critical perimeter. So let's call that U naught. Then we have, it is obtained by the perimeter of the column plus 8 multiplied by 1.5 d, right? So we know that the column is a square column, so we have the perimeter to be 4 multiplied by the length of each side, right, plus 8 multiplied by 1.5 and the depth of that structure, as we have obtained previously, would be 240, right? That's exactly what we applied previously. Now, but by observation, we might not be able to obtain what exactly we would want to obtain using a 300 millimeter deep pad base, right, because of the punching effect. But I would like to show you what result we would obtain using this expression. So if you have rightly entered your values into your calculator, you should have a value of 4480. Yeah, so and you would use this in millimeter to obtain the area within the critical perimeter, right, which is U naught. We use this formula squared, being a square column, right? So we have 400 plus 3 bracket 4, 240 rather, 240 squared, right? And this should give 1.25 multiplied by 10 raised power 6 millimeter squared, right? So to obtain our force from here, our force V, right? So I just call it force V, or however it is you want to call it, is obtained by multiplying the earth pressure by the difference between the base area and the critical area. So we have, from the earth pressure, we have 216.7. We have 9 minus the critical area. That's 2 point, is it 2 point now? That's 1.25. Having converted that one to millimeter square. You know, this is in millimeter square. This right here is in millimeter square. So we have to convert it to meter square. So we have 1.25. Right. So this should give us a value of, if you had entered that correctly, it should give you 1679.43 kilonewton. Right. So from here we can apply the formula for our normal stress, since we have all other values here. So we can use the critical perimeter now, multiply by the depth. Now the load we obtained formerly, that's going to be the force we obtained, rather, not the load. That's going to be 1679.43 multiplied by 10 raised to power 3, converting that to Newton. That's what we had, 10 raised to power 3, divided by the critical perimeter. Now the value you have for the critical perimeter, which is 4480 multiplied by the effective depth. Now if you do this appropriately, you should have 679.43 you should have 1.56 Newton per millimeter square. Right, but this is the next thing to do. We have to compare the value of our V to that of VC. So in your code of practice, clause 3.5.5.2 discuss the provision that we'll need to consider in this regard, whether it's been less, V is less than VC or greater than VC. Right, so you need to check the code of practice BS8110 for that application. But in this case now, let's confirm what our relation is in this case and see how we apply our result. So for VC, use the formula 0.79 divided by, we have 100 AS over BD, 1 over 3, then 400 over D, 1 over 4. Right, so with this you can get a value for your critical shear, your VC. Right, so this is from the table 3.16. Table 3.16 also would give you the provision for shear, give you provision for shear. Right, so and we know that the value for this is 1.25. right, we have obtained our area of steel formally before now, so you can just copy down and apply it to your result, then will be good. Right, so a little time, let's put it in, let's put those values in, then we'll have our result. So all right, if you have rightly done that, you should have a value of 0.68 Newton per millimeter square, right? Or I think 0.69. Right? So but you would notice that whenever our FCU is greater than 25, the value of our VC would need to be multiplied by the FCU in question divided by 25 raised to power 1 over 3, so that we can have our final VC, right? You do not want to forget that, so that your answer will be correct. So you have 0.77. Now we see that our V is greater than VC. That is to say that our punching shear is not okay. That is, this structure will fail, or this element rather would fail due to punching effect, right? So we'll need to design against this scenario. So what are the basic things you can, what are those things you can do? So in this scenario now, the easiest thing you can do is to increase the depth of your footing and see how it affects the punching shear, right? So to do that, simply, if you increase the depth of that structure, or the thickness rather, increasing the thickness to about 500 mm. So our effective depth D will be equals to 500 minus the cover minus the reinforcement divided by 2. Then we have 440. Now if you go back to use all the equations and formulas we have used formerly to obtain first our critical perimeter, which is U naught, right? You should obtain a value of 6880 millimeter. For the area within the critical perimeter, you'd have 2.96 multiplied by 10 raised to 6 millimeters squared. Then for the force V, you'd have 1308.9 kilonewton. For our shear V, you have 0.79 Newton per millimeter squared. For our VC, you'd have 0. That's for our V, you have 0.43, and for our VC you have 0.48. So since V is less than VC, we can say our punching is okay, right? So simply we can agree that all our expressions now have been met according to the required design, right? So in case you have any question, you can just use the comment section, as I'll be there to give you the required answer and further explanation, right? I am Joshua the designer. We'll see you in the next video. In case you've not subscribed to this channel, you're new to this channel, use the subscribe button and like this video so that you can catch our releases as soon as they drop. See you. Bye.